So the final device we're going to look at is the UJT, okay? And what we have here is a circuit equivalent. Now notice schematically it looks very similar to a JFET, okay? With some key differences is that we have two base leads, right, and one emitter lead, okay? And this is what's going on as equivalent or the equivalent circuit of what's going on, right? So notice that we have basically a diode, right, and two bulk resistors and two bases. So what we're trying to do is provide a conduction. So essentially, we apply a potential here, right? And in order for the device to turn on, you need to make sure that the potential at this point, or VEB, is greater than VK by exactly 0.7. If that criteria is not met, this device is not going to turn on, okay? So, and what we call that is the peak voltage, okay, or VP. And basically, we got some, so VK, this point here, right, to solve for this point, or what the potential is here, most transistor UJT spec sheets will list a value of eta, okay? That's the Greek letter for eta, which is basically a nice way of saying it's the ratio of resistances, or more specifically, the ratio of the varying resistance within the UJT, which is RB1. Okay, notice it's just found by your voltage divider of RB1 over RB1 plus RB2. Okay, now if I want to know what the potential is here, if you grab that ratio, and this is no different than our voltage divider formula, if you grab that number, right, and you multiply it by the potential, right, in this case, you will find what that VK voltage is. Okay, now once you know that VK voltage, right, in other words, you grab eta, multiply it by VBB. Once you know that potential, if you just add 0.7, then you would know what the potential is here. And that's super important because that is your peak voltage, which is also the trigger voltage for the UJT. That's how it works, okay? Now, let's put this into actual practice as far as how it's utilized, okay? And one way is in a relaxation oscillator, okay? So now let's look at what we have going on here. So we have a potential applied, a UJT, and the output's taken here, okay? So the way this works is, now the point of the relaxation is just to produce these pulses to trigger, you name it, right? It could be used for a lot of different types of circuits. Yeah, it uses kind of this weird shape to pulse trigger things. So how this circuit works essentially is, we have a charging time constant that exists between RT. Notice he's variable, which means our RC time constant is variable. Okay. Now, what we have internal here, remember, we have a VK. And VK has got everything to do with the ratio of its internal resistances. Okay. And that's a potential. And notice that VDC is what's being applied across the UJT. So once VE gets to a potential greater by 0.7, VK turns on and it produces us an output, okay? Which is what we see here. Now, what we see here just so happens to exactly replicate the charge and discharge times of CT. So it's fair to say that once, and this is what's going on, once VE, right? So we're talking about the input here now. Once you apply the DC potential, he takes some time to charge, and that's what's going on here. He's charging, then he gets to a point, a VP. Now remember, VP is the point where it's VE is greater than VK by 0.7, so he turns on, and what you're left with is a spike, right? So you get an increase in potential on the output, right? And then what happens essentially is he gets to his thing, and now now we have a current path here. Once this current path is generated, this capacitor, once this connection is made here, this capacitor starts to discharge. And that's what you see here, discharging. And as a result, the device just gradually fades off, which suggests the internal resistance is now increasing. So at some point, you get to this point, the resistance gets to the internal RB1 goes to its smallest value, right? And then as things peter off here, RB1 starts to increase its resistance again, okay? Now, we can adjust when we want these trigger points to happen, or the value of him, or how long we want these pulses to occur by adjusting RT. If we adjust RT, we can change the time constant and how long it takes for the UJT to trigger an output pulse. And that's how basically the relaxation oscillator works.